reached almost 20 minutes. Okay. Is everyone with me?
Yes.
So f prime, the outer times the inner. X, f of x times f of x. X, f of x times f of x equals. I copy the first one. I cannot do anything to it. 1, 2, 3. 1, 2, 3. That's correct. Times. Here I have a product. It's a product of function 1, function 2. X times whatever. So I have to have plus. When I differentiate using the product rule, I have the first function. Oh, and that reminds me, on your homework, it's okay if you twist those derivatives, but once you make a mistake on the differentiation of a quotient rule, I cannot use it. I cannot give any credit. So please make sure that you go line by line with the solutions. It's not a good idea to twist them, but if you're, you wish to use the formula in the book, I'm 100% for it. So you can twist it here, it's no problem, but if you twist it in the quotient rule, you cannot get any credit because that would be incorrect. So first function prime is 1, so I have to copy f of this, x, f of x. 1, 2, yes, plus x. Now I have to differentiate this. When I differentiate this function, I have to differentiate the outer, and this is x, f of x. And of course, everybody knew already. I don't know why I even bothered to put the bracket here, because you knew I was going to run out of room. I knew that too. I was just making a point. Sorry about that. So one more time. First function prime is 1 times this plus this first function times this prime. So the outer function prime, now the inner function prime. But the inner function prime is a product. So I have to open now another set of parentheses, and at the end I will close. Again, if I don't have enough room, I will readjust. So now I have to differentiate the inner function. I have the outer, but now I have to differentiate inner. X times f of x. This again is function 1, and this is function 2. So I have to use the product rule. First function prime is 1 plus the first function times the second function prime. So what is the trick with this? Decomposing it slowly into piece by piece, if you want. Now I don't have a problem plugging in 1. F prime of 1 equals f prime of, I don't have to write it 1 here. I'm just going to say f, this is 1, of f of 1. 1, 2, 3. Times, I don't have to write 1 again. Oh, I'm here. Sorry. I'm here. Not there. From the equal symbol. So, perfect. Times, here, bracket. F of 1 of f of 1. So f of f of 1 plus 1, I don't have to write it, f prime of f of 1 times, I'm here, plus, times, parentheses, f of 1 plus 1 f prime of 1. Okay. So, go back. F prime of 1 is 2. So then this piece is 2. This piece is 2. This piece is 2. This piece is 2, but f prime of 1 is 4. Okay. So I have f prime of f of 2 times f of 2 plus f prime of 2. Let me write it before I look at it again. F prime of 2. And then times 2 plus 4 times 6. Okay, now I want f of 2. Where are you, f of 2? 3. 3. F prime of 2. 5. Okay. F prime of 3. And this is 3. And this is 5 times 6. 30. 33. Finally, f prime of 3 is 6 times 33. Is it 198?
Is that math right?
I don't know.
I'm looking at where the plus and the times right above your finger. I'm looking at the formula above and I'm just trying to match it all the way down.
Yes. So this is f of 2. This is the plus. This is f prime of 2. And this is 6 times 6. This is the 6. This is f prime of 2. And this is f of 2.
Okay.
And
Sorry,
this...
I got lost in all the symbols. Okay.
I know. I know. That's why I use my props. That's why I cover all this. Because, yeah, I completely agree. It's not a friendly function. Every now and then we have to see an example like that. So you can see how to handle it. So this product here continues here. But as you know, that will be the day when I don't run out of room. Of course, there is a bracket here. This bracket. So we have f of x and x times f. Yes, plus. Yes, sorry.
Other than for the sake of doing math problems,
yes,
where would this be used in like real life?
I always get that question, and I'm always prepared. Number one, if you are in a STEM program, you will need to be able to manipulate all these algebraically and using calculus in order to move on to more complicated situations in calculus too. That's number one. In other situations of depending on where you work, right? So if you need to determine max min, you're going to see the applications right now of optimization. Optimization is a huge field of mathematics, as big as algebra, geometry, trig, even much bigger than that, in which functions are and also multivariable calculus, not just one variable calculus. We only have one variable here in Calc 1 and 2, but when you get to Calc 3, you're going to be able to handle functions of different variables, more than one, 2 or 3 or more. So it depends on what you're trying to do. But the applications of this, for example, this particular problem is the algebra behind it, practicing the formulas, practicing the algebra behind it, and determining the rate of change of such a function. So if you're ever interested, depending on your line of work, if you're interested in determining the instantaneous rate of change of this function when time is 1, then you will have it here, 198 measurement unit over measurement unit, depending on what x is measured in and f is measured in. But the real-life applications will follow after we know the basic rules and how to manipulate algebraically and using the differentiation rules. You're going to be surprised, pleasantly surprised, I hope. We have a huge section in this chapter and a huge section in the next chapter on real-life applications. But if we don't know how to manipulate basic ones, you can say that this is above basic, and I have to agree, it is above basic. Although not difficult to handle if you're paying attention step by step. But you're going to see tons of applications shortly.
We'll see this in physics.
Say it again?
We'll see this in physics.
And physics, in chemistry, in biology, yes. Yes. Especially if you take physics after this without Calc 1 and Calc 2, you're going to have difficulties. Yes. Other questions for me? Anything else? It was a very good one. Anything else? Is there anything else you want to work on? Okay, so let's finish with another problem, if you'd like. Or is logarithmic differentiation clear? Do we want to see another example with logarithmic differentiation, or we can move on? Anyone?
Can we go over number 30 section
3.6?
Yeah.
Okay. Very good. Let me share and see where this is. This one?
That's in 3.5.
So in 3.5?
Yeah.
Sorry about that. So 30 in 3.5. This one. Okay. Is this the one?
Yeah.
Very good. Perfect. Good. So in this particular example, we're asked to find the equation of the tangent line to the graph of this at point P. So one option would be to just distribute here as 6y squared minus xy squared equals x cubed, and then differentiate implicitly. What do we get on the left-hand side? Can anyone give us the left-hand side?
12y dy dx.
Awesome. And now careful, because there is a minus sign.
Minus y squared.
So we have function 1 and function 2. Very good. Y squared plus.
And then plus x
Times
2xy dx.
Very good. Awesome. The reason why I did that is because we don't want to forget to distribute a negative sign later on. The right-hand side is friendly and nice, is 3x squared. At this point, we will distribute the negative sign. So 12y dy over dx minus y squared minus 2xy dy over dx equals 3x squared. This piece has to move to the other side because it does not have the variable. And if you try to add these, you can't. They're not like terms. But what we can do is simply factor out the variable. And the right-hand side is 3x squared plus y squared. Can anyone give us the quantity in parentheses?
12y minus 2xy.
Very good. And finally, we have dy over dx.
Here we have 3x squared plus y
Right.
in the numerator, and 12y minus 2xy in the denominator.
Thank you very much. That's true. At this point, I'm basically interested in finding the value of this expression, which is the instantaneous rate of change at p, when x is 2 and y is the square root of 2. So when x is 2, y equals the square root of 2. So 3 times 4, 12, plus the square root of y squared, which is 2. 12. Y is the square root of 2. And negative 2, and this is times 2, the square root of, so times 2, the square root of 2. So the numerator is 14, the denominator is 12 minus 4, they have the same radical, so they are like radicals. So 12 minus 4, 12 the square root of 2 minus 4 the square root of 2 is 8 the square root of 2. I will rationalize with the square root of 2. And let's see what happens. 14 the square root of 2 over 8 times 2. I'll simplify. And this is it. 7 the square root of 2 over 8. This is the slope at P. So now in order to determine the equation, I have to write y minus y1, y minus y1 equals the slope times x minus x1, where the slope is 7 the square root of 2 over 8, x1 is 2, y1 is the square root of 2. So y minus the square root of 2, 7 the square root of 2 over 8, and x minus 2, I distribute. So 7 the square root of 2 over 8x, and when I distribute here, I get minus 7 the square root of 2 over 4. But then I have to add the square root of 2. So I multiply the top here by 4. 4 the square root of 2 minus 7 the square root of 2 is negative 3 the square root of 2. Negative 3 the square root of 2 over 4, 7 the square root of 2 over 8, and y equals tangent at P. Very good problem, thank you.